physically, what is it? Current. That's the current. And so, in fact, it's saturated at 1 amp. Right, so you can say, okay, my limit's going to be 1 amp. Keep it away from 1 amp. You might say, I really want to keep it away from 1 amp. So what am I going to do? Put my penalty at, or my max at 0.5 or 2. So it means this thing gets bigger. It means it's going to really try to keep it away from that saturation. The bigger you make R, the more it's going to restrict the bigger R. What do you say about energy in the system? Power going into the system. There's your minimum. Don't try so hard. It's all current. As much as I can. Okay. So on a test, say what they are and then justify what you chose here. If I'm saying its max is this much, therefore the penalty will be this. Remember the curious thing that happened is if I have these, whatever my Q and R is, and I increase them equally the same amount, what happened? No change. I'm increasing Q and R exactly the same amount. Double Q, double R. My gauge came out exactly the same thing. And that's the nature of the problem. Kind of not obvious maybe in that value, but sort of different. And in bus control, we actually use that feature. So I don't have to specify each one of these. I only specify one of them and scale. So that's the difference. Okay. That's about all I'd expect to do for this optimal control part. So we have to specify these. We install it, map that, and implement once you get the gains. What's the difference? I get the gains through a recovery equation. I design my regulator. How do I get my regulator? Exactly the same way. No difference. The only thing I've changed is how do I figure out, how did I calculate where gains were? Only difference. Yeah.
Are we going to do any tracking?
Inputs, yeah, you should be able to at least know how to scale input. Do that. So if I have, really, we usually do it in this form. Here's my regulator. And my regulator is related to Kx. So if this is some desired state, well, what am I getting here? This is scaled by that. So the simple case here, what's A? Let's say my inputs are all the states, make it really easy. But I have inputs of all the states. So I input a position and velocity. Let's say for second dishes. Could I do that? No, I go to a certain position, I go to a certain velocity. Is that possible? Mathematically it is. I can have multiple inputs. I can have input flows. In that case, it's okay. Or this might be just a subset. Subset of gains to whichever subset of states I want here. So maybe it's just X1 I care about. Right? I'm still feeding back this, so whatever I have in K1 might be just that. So now I've matched up. So this is X times K1, X times K1. Yes, there. to the right dimensions. Because really what I was finding here, this is a x desired, or it's x one. Plus k2, x2, whatever the other one here. So what have I done to x1? That's that. Well, it is an error signal. That's what have I done to my state. Redefine the origin. Instead of the origin being 0, origin is just x dot, x desired. You shift the origin. Linear system, that's perfectly fine. In a sense, you might think with this is really 0 minus plus x2, k3, 0 minus x3, or something. What's changed? Okay. So, of course, input that's primary in. And you can do the putting in integrators and that kind of thing, but I also have to look those up to remember how to do those. Never remember that. I just have to look up and work it out. So it can take a while to work it out. Simple scaling should do it. Yeah.
To what extent, for the exam, do you want us to know the block algebra?
Should be able to do this where I have two signals here. Let's say A1 and A2, that this is equal to A1 minus A2. About that much.
Okay.
You should know that that's the input, that's an output. All right. Block diagram is basically it's a graphical way of an algebra. You should be able to, and we stress it more, the first exam of getting the state equations. Here's some differential equations. Getting the state equations, not as much emphasis here, with one exception. This test was probably more of those. And that's the structure. Here's our basic set of equations. But we can have a disturbance in noise. This is for the Calvin filter. So this is part of the Calvin filter you have to know, at least the structure of what's going on here. This is sensor noise. And this is disturbance for unmodeled states, unmodeled states. Effects. Unmodeled effects that we ignored from the A and B. So you know how to get A and B. If I had a set of equations, they are with 2 times W, 1 plus 3 times W2, so forth. Could I get what G is from that? Let's take a simple set word. state equations for us, the AB and G matrix. Let's look at this, please. Try to do that. Let's see what we've got. We can write that, figure those out. We got the A matrix, I think the easy. A matrix is one. Minus 1, 1. 2 minus 1. Right. B matrix. 4, 0.
Sorry, what's W1 and W2?
Two different disturbances or unwelcome effects.
So G is a
I have two W's. W1 and W2.
So G is a 2 by 2.
She is a 2 by 2 in this case. What is it? 2, 0, 1, 3. W is W1, W2. So looking at state equations, you should be able to figure out G. Basically, it's nothing different than what we did in the very first class. Yeah.
What's G stand for?
It is like a B matrix. It says, how do these disturbances or unwelcome effects affect our state equations? So if this is an input, but it's undesired input. This is the desired input. U is something I'm trying to use. It's going to be my KX. W is something I can't do anything about. There's noise, disturbance, other problems I have here. And usually I'm trying to present it to minimize those effects, and that's what counter filter does. Go through detail, but it tries to minimize the effects of W. Another question you guys should be able to answer. All right, what's good about counter filters or these optimal methods? When you're talking about regulators and counter filters, what's good about this?
They filter noise, or?
Well, pole placement filters noise too.
Okay.
Yeah. All observers are filter groups, they will filter noise. But why would I do, the Riccati approach versus pole placement approach? What's the difference?
Weight or penalize different states?
Well, pole placement I'm doing what?
Arbitrarily setting them?
Sure. Well, I'm choosing poles, desired poles. By choosing desired poles, what am I doing? Choosing a desired time response, desired frequency response. Right? But with the Riccati approach, what are we doing?
Optimizing the time response?
We're trying to,
Focus on the states.
yeah, really a steady state response. We're trying to make sure the states stay where I want them. I'm not making a time response. I'm making it more steady state, trying to make sure that these states stay within this amount, or the input is within this amount, and so forth. And then do a pole placement observer. Okay. Why do I do that? What we're trying to do is a pole placement observer. Purpose of an observer. Yeah.
You're setting up the creative models estimated.
Well, I'm estimating the model. First of all, main thing, I'm estimating the model. Right? I'm really estimating my states. Right? I'm using the estimated model to estimate the states. Why do I need to estimate them? Why do I want to estimate the states? What do you need to? What's that? Can't direct a major. That's actually the case of the pinhole, the lab. We cannot direct a major to the velocities. So we have a forward observer on that we designed that has estimates of both position and velocity. And we did a full order one because it's easier to do a order one. So it's the estimate states. And then replace the poles for what purpose? Estimate quickly, faster than the pole. Why would I use the Kelvin filter approach? What's the advantage of that in the pole system?
You said the accuracy of your estimates.
Yeah, accuracy is due to what? The noise and disturbances. I'm trying to minimize the effect of field as best as possibly can. All sensors have noise. And I know what this noise is. I'm going to try to minimize it. We have these unwelcome things and disturb. I'm going to try to minimize their effects. The disadvantage of that, though.
Time response.
Well, what about the time response?
We don't set it right.
I don't know where the poles are. Right? And if I have a lot of noise, I could have potentially observer poles that are very slow, even slower than my controller poles. It could be a problem. Right? So the advantage is, yes, I'm going to have the best possible filter to get rid of noise and things. Disadvantage is, I may not have a very robust system. So, yeah.
You always want to put your observer poles on the real axis.
No, not necessarily.
Benefit.
Yeah, what is the benefit of, the question is putting the observer poles, make them all real, or make some of them complex? Why would you choose one or the other? Why would you make them all real?
Critical thinking, classes.
Yeah, I don't have any overshoot, so it's like I overestimate my states to get my best estimate of the states. Where, if I have a little bit of underdamp too, what's the advantage of that?
Faster response.
It might be faster, but realize I really overestimate it. So is it a problem with you? Depends on your system. Airplane cruise control, maybe not a big deal. American middle, could be a problem. Maybe I get overcut. Okay, it's usually not a good thing to do, right? So it depends on your system. Airplane, if it overshoots a little bit, yeah, okay. Maybe a landing. Yeah. Even then, we can overshoot a little bit. We get a little bit of shock focus in this landing gears.
One question, first off, are we allowed notes on this?
Yes, we're going to do it like last time. Paper notes, no more. All right. So, the nice thing about paper notes is a great study guide. Nothing more than 2x2s. I won't kill you with the invert a 4x4 matrix. And it is cool and neutral country. Well, but everybody thinks what actually comes in linear algebra stuff these days. I don't know. I've gone down to this using Excel for calculating that. Yeah.
Do they use state space and adaptive control?
Yes, very much so. Adaptive control. What are you really doing with what